ninth element in the periodic table, located in period 2, group 7. It's classified as a halogen because it's one electron short of having a complete outer shell. It's also located within the P block of the periodic table, as its electron configuration ends in the subshell P. Today we'll be focusing on fluorine-19, which is fluorine's only naturally occurring and stable isotope. It has 9 protons, 9 electrons and 10 neutrons. However, there are also 17 other known isotopes of fluorine. Fluorine has many chemical and physical properties. It's a gas at room temperature and it has a low melting and boiling point. It has an atomic radius of 147 picometers and a core charge of 7. It has a first ionization energy of 1,681 kilojoules per mole and has an electronegativity of 3.98. Fluorine is also the most reactive of the elements in the periodic table, meaning it isn't found in nature in its pure form, often in minerals in the Earth's crust, making it very hard to isolate. But what makes fluorine so reactive? Reactivity in chemistry is a tendency of a substance to undergo chemical reaction, either by itself or with other elements. This causes fluorine to form bonds with many of the other elements in the periodic table, including some noble gases. Because fluorine is a nonmetal, it forms both covalent and ionic bonds with other elements, including itself. Fluorine is one of 7 elements that naturally occur as a diatomic molecule in its gaseous state. This is an example of a covalent bond, as both atoms are classified as nonmetals. A covalent bond is formed when outer shell electrons are shared between the 2 pairs of atoms, as can be seen in the diagram. A single pair of electrons are shared between the 2 fluorine atoms, demonstrating a single covalent bond between them. Due to the fact that both atoms have the same electronegativity because they're the same element, the bonding pair of electrons can be found exactly halfway between each atom. This means that fluorine is a nonpolar molecule, as an equal number of electrons exists in the orbital overlap and are not pulled closer to one atom over another. Fluorine gas is nonpolar, meaning the only force holding the molecules together is the weak dispersion force. And as there are only 2 atoms in the molecule, it exists in a linear shape. Because fluorine exists as a diatomic molecule in its pure form, when referring to the properties of fluorine gas, they are the same as the properties of fluorine in general, although you are only talking about one atom. Fluorine gas is flammable, pale yellow in colour, and has a pungent odour. It doesn't conduct electricity, and many of its reactions are sudden and violent, igniting many materials. Fluorine gas in its pure form doesn't really have any individual uses, however, it does combine with other elements to form compounds such as Teflon, which is used as a non-stick agent in cooking. It is also found in chlorofluorocarbons, which were found in aerosols before discovering they pose an environmental threat leading to their ban. Fluorine also forms ionic bonds when a metal such as sodium gives up its valence electrons to a non-metal, fluorine, now both ions having full outer shells. This causes the metal to become a positively charged cation, as it has lost an electron, and the non-metal to become a negatively charged anion, as it has gained an electron. The oppositely charged ions are now attracted to each other, forming the compound sodium fluoride. Due to the non-metal, like fluorine, having a high electronegativity, and metals like sodium having low electronegativity, the fluorine atom easily takes sodium's single valence electron. Sodium fluoride, like all ionic compounds, is structured in a crystal lattice with alternating sodium and fluorine atoms in a cubic shape. The compound is a white powder which is soluble in water with a melting point of 996 degrees due to its strong ionic bonds. It is often used in water fluoridation systems and dental products such as toothpaste to prevent dental cavities. The advantages of my model include: you can move the electrons to effectively demonstrate the bonds, there's an obvious nucleus to electron ratio, and there's a clear differentiation between the 2 elements. The limitations: it doesn't properly show the spherical cloud of electrons, the particle movement is not consistent, and the nucleus to electron ratio is not exact. The use of a cake for the nucleus and chocolate melts for the electrons demonstrates the different sizes of the particles in an atom, as well as engaging the audience by showing the practical application of fluorine in the connection between dental health and its presence in dental products. Let's come back to our question. What makes fluorine so reactive? It mostly comes down to its electronegativity. Fluorine is the element with the highest electronegativity, meaning it has the maximum tendency to attract valence electrons due to its desire to complete its outer shell. Other elements in that group also need 1 electron to complete their outer shell and therefore also have high electronegativity. However, because fluorine's electron shells are closer to the nucleus than any other element in that group, the pull on the atom's electrons is stronger than any other element in that group, and thus the rest of the periodic table.